A research team led by Tao Sun, Associate Professor of Materials Science and Engineering at the University of Virginia, has made 2 discoveries that can expand additive manufacturing in aerospace and other industries that rely on strong metal parts. Additive manufacturing has contributed to aircraft production for years, as reported by the Association for Manufacturing Technology. However, additive manufacturing also generates defects in the microstructure of a finished part, limiting its role to the fabrication of ductwork, interior components and other non-critical parts. Additive manufacturing of safety-regulated parts will help the industry achieve its aspirations for efficient and stable supply chain management, as well as fuel savings and emissions reductions that accompany a lighter aircraft. Sun's team and collaborators have discovered why structural defects occur during the additive manufacture of parts made from a high-strength, lightweight titanium alloy widely used in aerospace applications. They present a process map, the blueprint the machine uses to create a part, to help manufacturers avoid generating defects during a common additive manufacturing technique called laser powder bed fusion. The team's paper, "Critical Instability at Moving Keyhole Tip Generates Porosity in Laser Melting," is published in the November 27 issue of Science. Kang Zhao, who was a postdoc in Sun's research group at Argonne National Laboratory and now a faculty member in the Department of Mechanical Engineering at Tsinghua University in Beijing, first authored the paper with colleagues from Argonne, Carnegie Mellon University, the University of Utah and the second author, Niranjan D. Parab, was also one of Sun's Argonne National Laboratory postdocs, who has since joined Intel. The research team focused on the 2 most important conditions of the additive manufacturing process: laser power and scan speed. How these 2 conditions are set and interact is captured in a power-velocity process map. Similar to a conventional map, the power-velocity map sets boundary lines between areas in which to work and areas to avoid. The power-velocity map can be divided into a good zone and 3 bad zones. If the manufacturer stays in the good zone, the build will likely yield a high-quality part on a consistent basis. 2 of the bad zones are easy to recognize. One is represented by a lack of fusion, evidenced by unmelted powder because of deficient laser power density. A second bad zone is represented by balling, when a single printed line rolls up on itself, signaling that the laser is moving too fast. Sun and the team focus on Zone 4. In this zone, parts come out of the build process with tiny holes, a structural defect called porosity. These tiny holes appear inside the material, making it hard to see and control. You could print multiple test lines, and you still would not know by examining the part surface if porosity is occurring underneath, Sun said. Porosity defects remain a challenge for fatigue-sensitive applications, such as aircraft wings. Some porosity is associated with deep and narrow vapor depressions called keyholes, which occur under high-power, low-scan speed laser melting conditions. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.